Okay, so let's talk about those homework questions. So, question 1. This is a very typical IB question style format. Morning, Quinn. Where you have a question, you have 3 statements, and then you have answer choices based on those statements. So it's asking you which of these are true. So the way I recommend going through this is look at each statement and evaluate it and give it a check or an X or whatever. And then hopefully you can at least narrow it down so that you can make a more educated guess as to the answer choices. So you're going to get, 1 and 2, 1 and 3, 2 and 3, or all of them. So this is you're going to see a lot of this in the multiple choice section. And the statements can sometimes be, you have to kind of close read them, because sometimes there will be particular words in there or particular words in the question that kind of determine the accuracy of the statement. So let's start with statement 1. Molecules gain kinetic, as ice melts at 0 degrees Celsius, molecules gain energy and temperature increases. Is that true or not true? Why is it not true? Right, because if we go back to our heating and cooling curve, when ice is melting, the temperature is not changing, right? And it says in the question at 0 degrees. So the temperature is not going anywhere because it's at 0 degrees. So these are little things that will trip you up because, yes, generally when we add energy, the kinetic energy goes up and the temperature increases, but not when we are in the middle of a phase change. So that is the trick to this question. So this would be no. Added energy overcomes hydrogen bonds between molecules. True or false? Thumbs up, thumbs down. Yes, thumbs up. Now, this is important because when they say ice, they're talking about frozen water, right? And frozen or water in general has hydrogen bonds, so being careful to pay attention to that. I don't expect, but they might give you some sort of question about, some other solid that maybe doesn't have hydrogen bonding, and you'd have to pay attention to that. But water does have hydrogen bonding, and if you've forgotten everything about IMFs, don't worry, we're going to go over it, okay? And then molecules gain sufficient energy to move from fixed positions. Thumbs up or thumbs down? Right, yes, thumbs up. Now, if this was going from a liquid to a gas, this statement would be incorrect, but going from a solid to a liquid, it is correct. Okay, so just be careful as you're reading these. Feel free to annotate questions. You can write all over your test booklet, whether it's an in-class quiz or whether it's the final exam next May. So I like to annotate stuff. Obviously, if you feel really confident about this, maybe you don't have to write anything down. You don't even have to do the checks and the X's, but it can be helpful, especially if you want to go back to that question later. So if you want to flag that question for going back to it later, having already put your thoughts kind of on the page can be helpful. So this is going to be 2 and 3 only. The most common wrong answer is D, because people, the question 1 is correct, but not while ice is melting. Or statement 1, sorry. All right, and what do we call the change of state from a gas to a solid? So give me 1 finger for A, 2 for B, 3 for C, 4 for D. Hold up your hand. Yes, 2. Okay, good. And I am hoping that by the end of class, I'm going to inch this up a little bit. Oh, it's starting. Yeah, by the end of class, somebody remind me to give you a minute to come up and look at the iodine, because I've got that going, and it should go more strongly over the course of the period. Any questions on this? Okay, so you are going to turn this in on your way out into the turn-in bin. So the homework is just, I'd like you to do it. If you don't now, I understand. So I thank you so much for all of your feedback on the warm-up yesterday. I read them all. I really appreciate it. I took notes. And some folks said they were concerned about the workload with regular homework. If there are days when you have a lot of other work and you just can't get the homework done, we're most of the time going to go over it in class. So you can just write down the answers then. And even if we don't, if you give it to me by the end of the week, or if you need more time, just let me know, okay? It's not supposed to be a punitive thing. All it's supposed to be is a chance for you to practice something, 2 questions, very quick, in order to kind of solidify stuff when you get home. Or later in the day, whenever later in the day is, maybe you're waiting for practice in the afternoon and you take a look at it. So don't stress about the homework. It's really there to give you another easy grade and to reactivate your memory of the material. So if it doesn't happen, don't worry about it. But please try to do it every night, and please turn it in so that I can put that in the gradebook. If you ever have a question about something that I marked that either we talked about or you had some extenuating circumstances, just let me know. Okay, we'll figure it out. Okay, great. All right, atomic structure. I will admit that I have not actually looked at the whiteboards yet, but I will pull those out at the end of this unit so that we can sort of compare what you remembered before to what we are reviewing and relearning. So pretty much this whole, yes? Oh, okay. Yeah, so yep, there's a 1.2 and there's also a 1.2 HL, so make sure you have both. Thanks for that. And thank you for saying that promptly so that we could get that figured out before we get halfway through the class. So quick thing about that, the study guides are written, the teacher who writes the study guides writes them so that you also need one? Oh, you have 2 of the HL. Okay, thank you. Okay, do you have a regular one? Yes. Okay, sorry, you don't. Okay. Yes, you do. Okay. Yeah, it's a little confusing. Okay. You have an extra SL? Okay. Do you have an HL? No. Okay. Okay. We'll figure it out later if anybody still needs the HL packet. All right, so there's that. Oh, you're good? You have it. Okay. All right. Great. Don't worry about it. We'll figure this out. So there's the teacher who does this, who makes these, breaks them up into little pieces to make them more kind of digestible. So it means you're going to have a lot of these. I will tell you after we get through something, if we say take a quiz, and then we're going to go back to part of it later, I will tell you to keep it in your active folder in case you have kind of like a system for not keeping every single piece of paper. I will try to let you know if we're going to be coming back to it. Because there are some cases we're going to jump around a little differently than the way he writes it. So the 1.2 and the 1.2 HL, there's actually some overlap there, so we're going to kind of seamlessly go right from one into the other. And that's going to happen kind of a lot because the standard level curriculum is included in the higher level curriculum. The higher level curriculum goes a little bit more in depth, but sometimes in the HL packets he'll put in like review stuff from the SL in case you're, say, doing standard level curriculum one year and then doing the higher level curriculum the next year. There's lots of ways people do it. So he's trying to make it flexible. That means we have lots of little paper packets that sometimes have overlap. Okay, so basic atomic structure, nucleus, electrons, right? All the mass is in the nucleus. Protons and neutrons have a relative mass of 1. Electron has a relative mass of 0. It's, I think it's 1/2000th, roughly, of the mass of a proton. So we call it 0 for the purposes of calculating the mass of an atom or of a set of atoms, because it's effectively 0. Even if you have element 118, 118 electrons are not going to add up to even close to a proton, the mass of a proton. So we just ignore the electrons. They do have mass. It's just very, very tiny. We're going to talk more a little bit later about the energy levels, but we do have the electrons and energy levels in the atom, which we normally show with this Bohr model diagram. And you've seen this before back in honors chemistry when we did the build an atom simulation and various other pictures of atoms. You're probably familiar with this idea of the circles around the nucleus. We know that's not really what's happening, and we'll talk more about that later. The nucleus is tiny. It's got all the mass, but it's tiny, tiny, tiny. So if we have one atom, say a carbon atom, the size of a soccer field, the nucleus would be the size of a marble on the center circle. Okay, so that's how much, relatively much of the volume of the atom is taken up by the electron clouds. Okay, and we assume, unless we're given information about the charge or the number of electrons, that the atom is neutral. Okay, if we're given a charge or if we're given some information about the number of electrons, then we can say something about it. Otherwise, we're assuming it's electrically neutral, meaning we have the same number of positive protons and negative electrons. Okay, so that's the assumption we make unless we're given other info. Okay. Questions? Okay, you've heard of these numbers before. We've talked about them in honors chemistry. The atomic number and the mass number. The letters are new. You can usually get by without remembering what Z and A are. It will become clear from the context of the question. But just so you're aware, they use the letter Z for atomic number and the letter A for mass. And that's going to come up again in a little bit. And so we can draw a Bohr model of an atom. We can write it in a variety of ways. One of the ways we can do this is what we call the nuclear symbol notation. Okay, that is what we're showing here. So often you will see it as the atomic number on the bottom, the mass number on the top. Sometimes you'll see it with just the mass number on the top and no atomic number. Why would we leave out the atomic number on that notation? Amber?
Because the atomic number would be 1.
Close. Yeah, you're on the right track. But for fluorine, yes, because it's the number of protons, and that's going to be the same for every atom of fluorine. So it's kind of redundant to put this 9 here, because fluorine is always 9. If it's an F, it's 9. Okay, so sometimes you'll see it written, sometimes you'll see it omitted. Okay, you will always have, on any test, including the final IB exam, you will always have access to your data booklet, which has a periodic table in it. So you're not going to have to memorize atomic numbers or memorize the elements. You will always have that available to you. But it does help when you get kind of used to certain elements. You will find yourself memorizing some of the atomic masses, some of the atomic numbers. You'll just kind of know where they are on the table. If you're not a memorizer, that's okay, because you're going to have it. You just want to practice looking for it. Okay. Okay. So mass number is the number of protons and neutrons added together. We could also call those nucleons. I don't think I've ever seen that on a test question, but they could throw it in there. That's because those are the things that are in the nucleus. So if you see that word, that's what it's talking about, protons and neutrons. If you have a symbol notation, it's pretty easy to find the number of neutrons, because you just subtract, and you have 10 in this case, right? So wrapping your head around the mass number, the protons and the neutrons, just that arithmetic. It's good to feel comfortable with that. Let's see. The mass number and the atomic number, both of them are always integers because it's a count. From our point of view, unless we're doing particle physics, you can't have half of a proton or a quarter of a neutron, right? So the mass number is an integer. The atomic number is an integer. Okay. We can always also write, and we'll get to this in a minute. We can also write the name of an atom or an isotope with what we call the isotope name, where we write the name of the element with a dash and then the mass of the element. Okay, and we'll get to that in a minute. So, I'm not going to make you fill out everything for all of the exercises. We're going to do some of them together, and some of them I'll give you the opportunity to do on your own if you want. Okay. Also, somebody asked yesterday for access to more practice questions, and I will get you guys on In Thinking tomorrow, where you will have access to a whole online course, including practice work that you can do on your own. I will very rarely assign stuff from there, but you will have access to it. Let me actually write that down. In Thinking Thursday. Okay. So we just talked about what atomic number and mass number are. How would you write the nuclear symbol notation for magnesium-24? Scout, start us off.
Well, first we have Mg.
Mm-hmm.
So atom lowercase b.
Good.
And then atomic number, that would be, the mass would be 24.
And where would that go?
That would be top left.
Okay. Okay. If we were going to complete this, what other number would we put there?
2. 2.
You think about the charge of an ion?
I think I am.
Okay, yeah, I think you are. What number would we put at the bottom? Yeah. 12. So atomic number is 12. We can omit that. The charge is going to be +2 when it forms an ion because of the octet rule. Yes. So I'm glad you're associating magnesium with 2, the number 2. That's good. Okay, and then iron 54. What's the symbol for iron? Anyone remember? Shane, is that a hand? Paxton. Fe, okay. Good. This is one of the ones, remember, that has funky letters that don't match the name. Why do some of them have letters that don't match? Yes.
Because they're already used by other.
Okay, in some cases, yes, they're already used by other elements.
I think it's like Latin.
Yeah, so a lot of these that were discovered early on, like iron, lead, tin, some of the other ones that were sort of common and easy to get at, they were given names early on, even before we had a periodic table. Those names were in Latin. So ferrous is the sort of root, and you'll see that sometimes when it's in common names like ferric oxide or ferrous oxide. Those are some compounds of iron with oxygen. Okay. So, what numbers am I going to put here? Annie? Mm-hmm. Yeah, I think it's 26. I don't have this one memorized, so yeah, it's 26. See, I don't even have the periodic table memorized, right? I have bits of it memorized. Okay, so if we had a charge on either of these, where would that go? Where do we put the charge? Good? Yeah, yeah. So if we had a charge, it would go here. We generally don't write a 0 if it's neutral. So, you know, you can write it, but there's no need. Okay, so if there's a number there, then it'll have a sign, plus or minus sign, and that would be the charge. So yeah, good. All right, questions? Okay, I got to keep remembering that this class is now 8:30. All right, so we've got a bunch of tables here looking at protons, neutrons, and electrons in based on these atomic symbol or nuclear symbols. You've done this before, most likely. I'm going to just walk through the first one in each table, and I'm going to give you a few minutes to do a couple more. Okay, I'm not going to make you fill out the whole table, because I think that would be a waste of time. But remember, the answer key to these packets is in Canvas, and so you can always, if you want to do all of the questions, you can do that, and then check your answers. All right, so atomic number for this one is the number on the bottom. The mass number is the number on the top. Number of protons, how many? Just shout it out. 1 proton. How many neutrons? 1. How many electrons? 1. Because we're not given any information about charge, so we assume that it's neutral. Same number of protons and electrons. Right? So you can go through this with as many of these as you like. Down on number 4, we've got calcium 40 with a 2+ charge. Notice that, and you may have heard about this in honors chemistry, the number comes before the sign when we're talking about charge. It's not a huge deal, but we are going to, probably next year, get into, maybe a little bit this year, oxidation states where it's flipped. So the reason for doing 2+ instead of +2 is that to indicate that we're talking about a charge and not an oxidation state. For something like calcium, it's going to be the same thing. Don't worry about it too much, but if you are wondering which is correct, when we're talking about charge, number first. All right, so atomic number here. What's our atomic number? 20. What's our mass number? 40. How many protons? How many neutrons? 20. 40 minus 20. How many electrons? 18. Okay. And you, for ions of elements that are in what we call the main groups, so group 1 and group 2, and then the last 6, so not including the transition metals, for most of these elements, here and over here, although not so much the post-transition metals down here, the charge is always going to be the same because of the octet rule. Yes?
The atomic number is the same as the number of protons, right?
Yes. Yes. So those are always going to be the same. But what you'll notice as you look at the number of electrons, and this is one way to sort of check yourself that you did the math right, is that they should match the number of protons in a noble gas, right? So 18 electrons is the same electron configuration as argon. So you're going to have either 2 or 10 or 18 typically for ions of those elements. So just if you see yourself writing 11 instead of 10, you know, do a quick double take there. All right, I'm going to give you about 5 minutes to do a few more of these. Feel free to talk to each other, work together. Excuse me. Yes.
It would be the same as the protons.
Yes.
We're assuming it's
Because there's no charge, so, yep. So when there's no charge, electrons and protons are the same as the atomic number. Biggest mistake people make, although I don't see anybody making it here, is using the mass number as the number of neutrons. Don't forget to subtract the protons.
Well, in some of them, yeah. But it's the mass number minus the atomic number. Like the mass number is the one on top.
Are these two the same?
No. I mean, occasionally they are, but they don't have to be. Okay? Yeah, so protons and electrons are going to be the same if there's no charge, but the neutrons are going to vary, and we're going to talk about different isotopes and why that is in a minute. So, yeah, mass minus protons gives you neutrons.
Is this right for the?
Yep, looks good. Good.
I made a mistake. No.
Oh, okay, good. You're doing the neutron. Okay, gotcha. Okay, great. That is all that matters, is that you catch yourself. All right, that just walking around, it's looking good. I suggest that you, if you are at all unsure or just want to check yourself, that you look at the answer key. I'm not going to post them all here because they're already posted in Canvas. Okay, and by the way, I will update Canvas tonight with the slides and the recordings that I have, and hopefully the sound will have worked. Okay. Moving on. Why is mass number important? Well, first of all, depending on the element, even the most common isotope might not have the same number of protons and neutrons. Up to about number 20, they are pretty close because that's where the band of stability is. You may remember that from honors chemistry. Nuclear chemistry is not something we really get into in this class, in this curriculum. Okay, so this is pretty much as far as we go, is talking about different isotopes and talking about relative atomic mass. Okay, so an isotope is going to be, and knowing the definitions, you'll see sometimes, especially in paper 2, there'll be, a 26-point question, and one of those points will be like, what's an isotope, or something like that. So knowing what the definitions are can be helpful. If you want to make yourself flashcards, might be a good thing. If you need materials to do that, let me know. I'm happy to, if you can't get your own index cards, I'm happy to provide those for you if that's a thing. or whatever else you need. I'll also later be linking to some Quizlets that will have some of the vocabulary in there as well. So same number of protons, different numbers of neutrons. Okay, so same atomic number, different mass number, same element. Okay, so you can't have isotopes of each other that are two different elements. Okay, so most elements have multiple isotopes. Carbon, for example, has about 3 that show up in nature. Carbon-12 is by far the most common. There's a little bit of carbon-13, which has 1 extra neutron, and a little bit of carbon-14 that has 2 extra neutrons. Carbon-14 is radioactive, and this is what we use for carbon dating. So we look at remains of organic materials. We can grind it up and look at the proportion of carbon-14 left since the carbon was incorporated into the skull or the whatever it is, and we can then determine the age of that fossil or decayed matter. But only for a certain period of time, because it does decay eventually to nothing. This, I'm not going to make you fill this out, but feel free to if you want to. The whole point here is that we've got 2 different isotopes. Everything is going to be the same except the number of neutrons. That's the only thing that's going to differ between them. Everything else is going to be the same. Atomic number of protons, in this case electrons because there's no charge. Okay, so, well, neutrons and mass number, I guess. Being able to write that symbol, figure out what the numbers are. If you're given the symbol, those are things you'll need to do. And I think, oh yeah, so because isotopes, different isotopes of the same element have the same number of electrons, and electrons, the movement or sharing of electrons is what makes reactions happen and how we make bonds. If we have the same number of electrons, we're going to react in the same way. So the chemical properties are going to be the same. Okay, how it reacts, how reactive it is, what kinds of compounds it makes with different elements is going to be the same for different isotopes of the same element. So you can have water that's made with hydrogen 2. It's called heavy water because the hydrogen 2 has a neutron, and each atom is going to be a little heavier. But because the masses are different, some of the physical properties are different. So the density is going to be higher because the mass of each atom is going to be bigger. But remember that nucleus is only a tiny, tiny part of the volume of the atom. So the volume is going to stay the same. The mass is going to go up. And so the density is going to go up as we increase the mass of the isotope. And then other properties such as boiling point and melting point are somewhat dependent on mass are also going to change. So it's a good mnemonic to remember that, well, not mnemonic, but a good thing to remember that isotopes of the same element are going to have the same chemical properties, but some physical properties are going to be different. Okay. And we'll talk more about mass and melting point and boiling point later when we talk about intermolecular forces. Okay. Questions on any of this? Right. You do not have homework today. Feel free to spend 10 minutes going in and filling out more tables in the packet. We will get into talking about relative atomic mass tomorrow.